Joseph, do me a favor and please check that the live stream is beginning in YouTube. It's supposed to be starting in a bit. All right. So it seems that we're live. I'm gonna wait a few seconds and then we'll start. Are we good, George?
I'm good.
All right. All right. Let me see. Welcome, everybody. This is the Space Talks by SEDS-UPRM. Today we have Mr. George Salazar from Johnson Space Center. He's going to be the first speaker for this semester. He was also the first speaker for last semester, and we had other talks. But you know, due to the pandemic, we couldn't do them. But he's going to be talking today about the importance of testing in certification of spaceflight systems, a very interesting topic. And I'm going to tell you a little bit about George. He is an experienced NASA engineer. He has worked at NASA plus over 35 years of experience in telemetry, communications, speech control, command and data handling, audio, displays and controls, intelligent lighting, product management, and systems engineering. He has worked with the Space Shuttle and the SpaceX Crew Dragon missions. And he's also been involved with the design of advanced telemetry, speech recognition, and intelligence systems, and he has received various patents for those technologies. He is currently serving at NASA Johnson Space Center, as I said, as the human-computer interface technical discipline lead to develop advanced human interfaces, as well as serving as the displays and control subsystems manager for the Commercial Crew program. He is also one of the mentors of our Rascal teams. He mentored the Empress team in last year competition, and he's also mentoring the Rascal team for this competition, the 2021 one. So without further ado, I'm gonna let it to George to begin his talk. Let's go.
All right. Well, thank you, Wilbert, and hello out there. I'm hoping that at least after this presentation that you walk away with at least one thing that you learned about certification of spaceflight systems. You know, even though I'm saying spaceflight flight systems, this actually could equally apply for other systems as well, whether you're in the category or industry of automotive or aeronautics or even oil and gas exploration. So I wish I had a lot of time. You know, this subject really involves a lot of information, and so what I try to do is basically try to provide a summary, for the lack of a better term, of what it takes to certify spaceflight systems. And you know, you used to hear people say, "Well, why does it cost so much? You know, to fly something on shuttle or to fly on Apollo or fly on space station?" It's because of testing. Because once you launch, there's no turning back. You got to make sure you've done all your homework correctly, that you've done everything that you can to possibly prevent a problem occurring. And so you test, and that's the part that I'm going to impart on you. You're looking at the what they call the V diagram. NASA has something similar to that, as I call it, systems engineering engine. So if you look at the left side of the V, and the reason they call it the V because it looks like a V, is that on the left side is the system definition phase. That's where you're developing requirements. You're developing architectures, you're developing trade studies and things of that sort. On the right-hand side is the implementation, where you start putting things together and you start testing. So and you would, this is kind of misleading because you're actually start testing early on the left hand side, and I'll share more with you that in this presentation. So my agenda is, why do we do test and measurement? You know, what's the importance of it? And for some project managers, especially the ones that have been around a long time, sometimes they hate hearing the word test and measurement because it's expensive. And there's a reason for that. It's because it takes a lot of effort to gather data to assess the performance of a system. The next thing I'm going to talk about is planning for testing at a very high level, and lessons learned. This is lessons learned. I'm going to give you a couple of examples where testing was not done and it was fatal. It was fatal to the project, very expensive. And then test and measurement activities. There can be a whole lot, but I'm going to give you kind of a very high level of that. And some final words. And again, you see there the my 50,000 foot level, because I could spend a whole semester talking about test and measurement. So, but before we get into the very meat of this, let's kind of recap what the V&V methods are. And V&V means verification and validation. So verification, it can be either inspection, demonstration, test, analysis method. And each method verifies a requirement, or and as you use these different kinds of these types of methods, it increases the rigor and complexity. Some requirements require more than one verification method. You may require test and analysis, or test analysis and inspection. It's very dependent on the requirement, and so you got to have very seasoned systems engineers in place to understand what has to be done to verify the requirement. And the verification of a requirement says, did we build the product right? Okay, so we want to make sure that we built the product right. That's verification. In other words, it meets the requirements from the standpoint of performance. Example, environmental. The system XYZ shall operate in the temperature environment from minus 40 degrees Fahrenheit all the way to 180 degrees Fahrenheit. Okay, that's an example. You do a test on that, and if you meet that, you met that requirement. So the different kinds of verification methods are inspection. So an inspection requires the use of human senses, as visual, auditorial, tactile. For example, verifying the physical features. One example is, like, for example, the avionics box, because electronics can be sensitive to electrostatic discharge, says something like the requirement would be the electronics devices shall have ESD tags on them. So how do you do the verification on that? By inspection. So if you got an avionics box, you should have basically a caution sign saying ESD sensitive. Okay, so verification by inspection. The vendor, whoever builds it, says, I'm going to put a ESD sticker on the very top of my avionics box. Let's go next to demonstration. So demonstration says it's a functional verification with the use of components or subsystems to show that it can achieve a requirement under specific conditions. So what does that mean? That means that you're demonstrating that this system basically can perform a specific function. So let's say, for example, you develop a spreadsheet, okay? And that spreadsheet is supposed to provide a means for computing the sum of different numbers and computing the standard deviation, stuff of that sort. So how do I verify that requirement? I'm gonna bring up my GUI, my graphical user interface. I'm gonna call up this spreadsheet. I'm going to put in numbers, and I'm going to see if indeed it does what it's supposed to be doing. That's pretty much a demonstration of a functionality of the system. Now let's go into analysis. Analysis gets a little bit more detailed, as that you're using mathematical modeling and analytical techniques to predict the compliance of a design to its requirements. And sometimes it goes along with test data. case in point, or an example is, let's say, for example, one of the biggies for NASA is radiation testing. And so we look at how many upsets have happened when we bombard this electronic box or this electronic card with high energy protons or heavy ions, and we see the number of upsets. So there's an analysis program. I think it's called Cream something, but it basically it takes that data and you perform analysis to see what's the mean time to functional interrupt. In other words, how often is this system going to hiccup in a radiation environment? That's very important for NASA, especially once we start going outside of the radiation belt, which protects us a lot from radiation. It's going to get more and more critical for radiation effects of electronics. Now here comes the biggie: tests. Test is very expensive to do. They use the component subsystems or systems using a controlled and predefined series of inputs, data, or stimuli to attain detailed data to verify performance. And usually analysis follows to verify a requirement has been met. So we test it, we measurement it, we gather data, we look at the data, and we start analyzing to see if indeed we did meet the requirement. An example is we do thermal testing, and during thermal testing, we basically there's a plot that basically changes the thermal chamber temperature from, let's say, minus 40 degrees to plus 100 degrees Fahrenheit. And so usually there's plateaus at different points. Basically, it stays for, let's say, at ambient for 1 hour, and you're doing functional testing. And then you go and then you start ramping up to the higher temperature levels, and then you do functional testing there. And so you gather all this data, and then you analyze it and say, did we or did we not meet this requirement that we're supposed to operate from, say, minus 50 degrees Fahrenheit to 100 degrees Fahrenheit? So the data basically is a defense whether that requirement has been met or not. So let's talk about validation, the bottom one here. More of a mission system requirement than that validates, did we build the right system? Now notice that there's a difference between verification and validation. Verification says, did we build the product right? The validation says, did we build the right system? And the product meets the needs of the customers. And that's important for the customer. So, let's see here. So in flight certification, it means that all requirements have been met through verification and validation. Not just that we built the product right, but that we built the right system. And I'll mention a little bit more about validation because that's still confusing to some folks. I know it was confusing to me when I first started getting involved with testing of flight systems. So let's talk about systems engineering and test and measurement. So flight certification requires proof of test and measurement as part of the evidence to certify the system for flight. In the end, we usually have these big powwows with a whole bunch of folks, and they say, okay, tell me or show me the evidence that tells me that this system is ready for flight. Most recent, SpaceX for Demo 2 mission. We had a big powwow, and we went through all the testing that they did. Qualification testing meaning design life of the system. Acceptance testing meaning workmanship. Was this system built correctly and with no workmanship errors? And so you're trying to show evidence that this system is ready for flight. The other thing is you have to remember that a requirement without a verification and validation method is just marketing. So if you got a requirement from the customer, or you develop what they call a derived requirement from a system requirement, you better have a method to verify that requirement. Otherwise, you're just, I guess, for the lack of a better term, you're blowing smoke. It's, there's no evidence, there's no way to verify that requirement. You have no way of proving that you met that requirement. And a test without a measurement is just a design demonstration operating at a point. There's no evidence to support design limits. So if you're not measuring while you're testing, you really have not done good systems engineering, good testing, because it's the measurements that are important, because it's that data that you have to refer to for analysis, for saying, hey, look at my data, I met the requirement. Flight certification requires good systems engineering to lead the test and measurement task. This is not trivial. A good systems engineer it takes to certify a system for flight, and they understand what has to be tested and what does not need to be tested. And that's important, because when you're developing requirements, some requirements do not require testing. Going back to the verification methods, you can also do inspection, you can do demonstration, you can do analysis. If you're going to put a sticker on a box, and I'm being extreme here, you don't want to test that. That's going to be too expensive. You're going to put a lot of people on the payroll to try to come up with something that doesn't have to do any testing. So the systems engineer, and especially the one that's leading the testing effort, has to understand what has to be tested and what does not. And it's not easy. That comes through experience. I have to say that, it was about maybe 12, 13 years of experience before I started to understand what requirements required, the different verification methods, as well as success criteria. Reduced risk in committing final design and ensuring defects are found early. That's another important thing about tests, and I'll say some more about that later in my presentation. But if you look at this diagram right here, you're kind of looking at the NASA, what do we call the product life cycle, going from what we call the mission review all the way to, let's say, something like typically we go to systems integration review and test readiness review. But all during this time, we have uncertainty, and we need to figure out what kind of testing is going to be needed to drive down that uncertainty. Because at the very beginning of a program, especially one we've never done before, there's a lot of uncertainty about a lot of things, about the requirements, about new technology that we're planning to use. And so it's part of the systems engineering process to drive those requirements down through testing. And that starts early. It does not start later. And that's a misconception sometimes about the V model, is that it shows that on the right-hand side of the V model, you start testing. And that's incorrect. You start testing as early and often as you can. And I'll think I have a presentation chart on that later on. It's a continuous process in the testing environment. So why do testing and measurements in a program or project? Is to capture defects early. Hardware is not perfect. Even though NASA buys these expensive electronic devices that cost $75,000, $250,000 for one piece, that does not mean it is free of defects. Also, it does not mean that the manufacturing process is defect free as well. People are putting stuff together. That means that there's possibly an error involved. And so during the development of both the designing processes, you're looking at the hardware standpoint, or rather you're looking at the hardware, and what you're looking at here is what they call the bathtub curve. And the reason for the bathtub curve is, you probably noticed that it looks like a bathtub, where it's at the very beginning, the burn-in phase, there's a high likelihood of a failure. But once it gets to a certain point in time, it's a constant failure rate, which is an exponential function, e to the minus t over mean time to functional interrupt, or mean time to failure, rather. And so you can compute the probability of success based on the constant failure rate. But it's only at the constant failure rate because, as you can see, it's horizontal all the way until it gets to a point where it starts wearing out. Once it starts wearing out, it's very difficult to compute that. You can use whiteboard models and things of that sort, but it's still difficult. Now let's look at the software. Um, Software is a tough one. The reason for that is because nothing fails other than the code that you wrote. And so if you don't test the code and you have errors, you get something like what looks like a sawtooth. All right. So early on, you develop code, and you can you can see that there's a high likelihood of failure. And the reason for that is because obviously you just develop code and it could be full of errors, okay, until you get it all flushed out. But then once you get all the failure rates flushed out, then there's an upgrade to the software. And guess what? You're going to start up with some more bugs in the system until you get those bugs out. And then you do another upgrade and you continue doing that to the point where you stop upgrading the software and it's just a constant failure rate. So it's a little bit different than hardware, but something to note that software has a different failure rate profile than hardware. And then the software, it's really the behavior of the software that sometimes causes unexpected interactions among system elements. And that's what you're trying to do during the testing phase, is to see if you capture those unexpected interactions that you weren't anticipating. A box by itself can be tested and work perfectly, but when you put that box with other systems, and I've been involved with that, once you put it with other systems, all of a sudden the behavior collectively changes is in the way that you weren't expecting. And that's part of testing too as well. You got to mature the design. You start early with the system, and yeah, you still don't have a good grasp of the performance. If you got human in the loop testing, HITL, HCI, human computer interface, you got that to consideration as well. So over here, Mr. Homer Simpson at the control panel in the human in the loop testing, this starts very early in the program. And in the chart that I showed you back at the very beginning of my presentation, human in the loop testing should start very early. You start with very primitive prototypes, but then you start increasing the fidelity of those prototypes. But during that time, you're trying to assess that interface from two aspects. You're looking at it from a skill-based human error, which could just be something like slip of action or memory lapse. Okay, so skill-based errors, and this is an area of human systems integration or human factors engineering, something not taught in most engineering disciplines unless you get into a graduate level. But I can tell you right now that if you can start learning about the human element, the capabilities and the limits of the human, you're going to be far ahead of some of your colleagues or fellow students that are working projects that are purely hardware, because for the most part, the human is always involved. And then there's some mistakes in human error. So the mistakes in human error are usually associated with new systems that the person is not familiar with, and they're trying to understand what the engineer wrote. So here's the problem. Sometimes the engineer says, well, I understand it. The person that's working with it or using it should understand it. And that's not so. Everybody has a different philosophy. They come from a different perspective when they see a system. So that's part of human in the loop testing, to making sure that you basically identify shortcomings in the interface design. Not so much perhaps the GUI interface, but maybe how they have to maybe execute a command. All right, and that's very important, because if they execute a command incorrectly, that could cause a catastrophic event. Case in point would be something like enabling a thruster, okay, to change the orbit of a spacecraft. Well, you don't want to have just one button and just press this button and they go to a different orbit. Maybe they didn't want to do that. Maybe they were at the wrong portion of the orbit to press that button. So rather than doing that, you're trying to prevent an error. So how do you do that? Well, maybe you do an arm and command. You arm the system, okay? So they press the button, enable thruster, and then you get a response. Thruster command enabled. You want to proceed. Now you got to go to step two. Step two is execute. Okay, so or sometimes even in more critical cases, you have an enable function, an arm function, and an execute function. Again, it's there's something called uh, uh, prevention of inadvertent commanding, and so you think about how you prevent inadvertent commanding. And there's been several airplane crashes because of that, because the system lacked that aspect of protecting against an inadvertent command. So, and also you're verifying and evolving requirements too as well. And as you test, you find out, my gosh, this requirement is just too stringent. We need to relax this requirement. This happened to me at one program. We had very tight requirements on the voltage variation of this particular power supply, and it turns out we didn't need to have it that stringent. So we relaxed the requirement during testing because we found out by relaxing that requirement, it was actually a lot easier to operate the system. Validate the models, digital twin. What do I mean by that? So validating the models basically says at a system level, this system is supposed to operate in a certain fashion. The digital twin basically provides an opportunity for during a mission, you can get data back, telemetry data from your actual flight system and compare it against your model. So your digital twin is your model. If you guys ever saw Apollo 13, that was NASA's version of digital twin. If you recall, they were trying to figure out how much current and voltage was required of the power of power systems on Apollo 13 to get them home. And so they started to do simulation at the ground systems to figure out what they had to do to shut off, turn on, and things of that sort to meet the requirement for power to get them home. So that was basically the ground system was the digital twin of the Apollo 13, and that's starting to become more and more important. I'm actually giving a presentation this coming Thursday at a conference in San Marcos, Texas, about what they call digital transformation, and part of digital transformation is the digital twin concept, which NASA is just. They're coming on board with that. It's very difficult to implement that, but we're getting there. And we want to involve the concept of operations. That's what ConOps is. So evolving the concept of operations is also important because as we start testing the system in the mission environment, and I'll say something later about this test as you fly, fly as you test, is that you're trying to evolve the concept of operations. When you first start early on in your program, you envision how this system's going to operate, but it may not be that way. As you start learning more and more, and you start maturing the system, you figure out, my gosh, we don't need to do this. We need to do this instead, or we need to get rid of this because we don't need it, and we do this later on in the time sequence. Reduce risk. You got the risk of technology that you're developing, and you got risk of software, you got risk of hardware, especially using new hardware that's never been flown in space before. But that's part of the testing that tries to reduce those kind of risks. And risk are a big, basically it's a big thing to a program. And any project that does not have a risk management plan, that does not have a some kind of risk management of some sort, I would say this project is in deep, deep, deep trouble. All right. All these things are the responsibility of the program and project systems engineering process, as well as project manager. So let's talk about there's basically two ways you can do test planning. Big bang testing, that requires little planning. Put everything together, build everything together, don't test anything, and just let's see what happens. All right. That's not the way to do a test. You do a more methodical systems engineering approach where you're doing basically build a little, test a little in an incremental fashion. Uh, if you want to get into systems engineering methods, sometimes it's called the incremental model. or sometimes it's called agile systems engineering as well. But you're doing it in a small incremental fashion rather than trying to put everything on the plate and hope for the best. That's not the way to do systems engineering. Test and measurement planning consideration, requirements development. It begins right here. This is something that I've seen in programs and projects. I'm involved with a lot of student projects in Texas called Texas Space Grad Design Challenge. And I can't tell you how many times the students and I can't fault them because they're not taught they're not taught or trained in requirements development. But it's here where it begins as far as developing the test and measurement considerations. How confident are you that we can meet those requirements? This is where you start developing verification methods. Okay, here's the requirement. The system shall output 80 dB SPL from the speaker. All right, that's a requirement, kind of a performance requirement. 80 dB sound pressure level. That's what SPL stands for. And so how are we going to verify this? Well, yeah, I would not do it by analysis. I would rather do it by test. And so during the test, you talk about the method. I'm going to test it. The description. We're going to use the audio facility. We're going to use this equipment. We're going to put the dosimeter to measure the sound pressure level at 1 foot away from the speaker. We're going to put a 1 kilohertz tone through the speaker system with a certain amplitude. And the success criteria says that if we come up with 80 dB SPL plus or minus 1 dB either direction, we've succeeded in meeting this requirement. From a validation point, you're actually looking at the operational requirements, but validation, for the most part, involves many requirements bundled together to meet those mission requirements. Test engineering personnel involved early on. You got to get these guys involved early on because you don't want to surprise them and say, "Here's our system, go after it." All right, it's not going to work that way. Here's an example. So I'm not sure you can read this, but if you look at each one of these different frames, you look at how the customer explained it. And so when they're explaining it, it looks like 3 seats with 2 strings on a swing. And then how the project leader understood it. So he put a rope on 2 different branches. And then the analyst designed it and basically said, well, hold the tree up and cut the middle of it and let the swing go through that tree. And then the programmer thinks you just tie 2 ropes to the tree. And then the business consultant thinks it's a sofa on a tree. And so you can see how progressively how everybody sees this requirement differently. And so that's the reason why you have reviews. That's the reasons why you do what we call requirements validation very frequently. Am I doing the right thing? Am I building the right system, Mr. Customer? And so you're meeting with the customer frequently. Otherwise, you're going to get billed. You see that roller coaster, you might get billed for what should be something less expensive. You're going to get billed for a roller coaster because the way you explain the requirement and the way the team understood it requires a whole bunch of effort, and it's going to get expensive. At the very end, you can see all the customer really wanted. If you really interrogated the customer, all they wanted was basically a tire with a rope tied to the tree. So this is kind of a simplistic example of sometimes how you can misinterpret requirements. And so it starts at the requirements. I can't tell you how many times that sometimes requirements are not given a lot of effort. Engineers have a tendency to say, "Oh, I think I know what he wants," and they start building and testing. And oh my gosh, this is, I think he's gonna like this because I like it. Blah blah blah. And you just don't do systems engineering that way. So you got to get the test engineering personnel involved early on and help them understand the architecture. So the architecture involves the structure, the behavior, and the components. So the structure, how this thing is laid out, the behavior, how's it supposed to behave, that goes back to requirements. How's it supposed to behave during the launch phase? How is it supposed to operate? How's it supposed to behave during the orbit phase? How is it supposed to behave during reentry? And the components, what are these components? What are their inputs, outputs, things to that sort? And then the way a system is used in the environment, this is where the concept of operations comes into play, is to help them understand the environment, also how all these components are going to be made up of, and give them an opportunity to understand how these tests are going to need to be performed. What's it going to take? This is part of costing. All right, these are some of the things that you got to be doing early on, so you can give a cost estimate, a good cost estimate. Sometimes, again, engineers just say, "Oh, I'm going to design this, this, and this," but they never think into consideration, okay, we're going to have to test. Well, what's it going to take to test? Well, we're going to need this equipment. Yeah, but what about test facilities? Yeah, we're going to need EMI. We're going to need radiation testing facilities. We're going to need we're going to have to develop a specific stimulus machine to stimulate the system as if it was in the actual space environment. All these things cost money and time and people. You got to factor that into cost estimation. If you fail to do that, you're going to fall far, far, far short in your cost estimation of your system. Built-in system testing, okay, ground support, special test equipment, like I said, test like you fly, simulation challenges. It's a challenge sometimes to fly a spacecraft system and doing the proper testing on the ground, because there are some things you cannot simulate very well in the Earth environment, like microgravity, and so you got to figure out ways how to do that. Maturity of the technology. TRL means technology readiness level. Do we understand the limits of the technology? Is this new technology? Have we ever flown it before? If not, what are the risks of using this technology? What do we have to do to modify this in order to operate in the space environment? You know, I hear people say, well, why don't you use commercial off-the-shelf equipment? Let's say Google and what's the other one? Amazon, they're using machine learning systems, for doing speech recognition and search engines, stuff like that. Well, that's fine, because they're here on Earth as a terrestrial system. They don't have to worry about the space radiation effects. So if you want to fly something like an NVIDIA general purpose graphics processing unit in space, you're especially if you're going to go to the moon and Mars, you're talking about some major risk associated with that. How are you going to mitigate those risks? There's something called technology readiness level planning, development planning, that basically you spell out how you're going to involve the technology readiness level. Over here to the right hand side, you see a thermometer with this is something that NASA developed back in the 70s, associated with how ready is it from TRL level 1. TRL level 1 is basically laboratory stuff. You're just putting together components at a laboratory workbench that basically is not nowhere near ready for flight system, all the way to TRL level 9, which basically is already operational, like, for example, space station. I can tell you that TR level 6 is a minimum requirement for preliminary design review. If your system or components that you're trying to mature are not at TR level 6, which basically you've tested in a relevant environment, then you're not ready. You're not ready for doing the PDR. You need to wait until you've matured the system a lot more. Technical performance measurements, I got a graph on that, but basically you're identifying key performance parameters to determine how well the system's meeting requirements. If you got a weight requirement, no more than 500 pounds, otherwise we can't launch, then you're going to have to keep track of all the things that are coming together that are starting to, that have weight, and you want to stay under 500 pounds. If you're going beyond 500 pounds, you're not going to launch. That's happening to a particular commercial partner right now. They're a little bit too heavy. So, yeah, you got to think about that. Okay, so test measurement and planning, the objective and scope of the test. What's your objectives? What are you trying to test? How much are you going to test? The interest and exit criteria. The interest criteria may be we got to have this piece of equipment, we got to have this facility, we got to have this test equipment, we got to have this piece of hardware with a certain amount of maturity. And the exit criteria basically says we verified this requirement, that requirement. So you have a specific entrance and exit criteria going into this test. Sometimes this is associated with test readiness review, TRRs. Test scenarios and success criteria. Yeah, test scenarios many times are related to what happens in a mission. Okay, we're gonna during the launch. What's the test scenario for the first 3 minutes of launch? What's the test scenario when we're approaching docking with space station, for example? What's the success criteria for that? Test equipment and the limitations. We got certain test equipment, but guess what? We cannot totally emulate all the stimulus that these spacecraft expects to is expecting for inputs. So what are the limitations? You have to identify that because you're gonna fall short in your testing if you don't identify those limitations. Measurements. What measurements do we need to capture and why? Why do we have to measure this pressure sensor? Why do we have to measure this vibration sensor, et cetera, et cetera? You have to everything you're going to measure and capture you have to say why we want to do this. And the reason you do that is because, again, goes back to money, all right? Money and time and people. You don't want to waste your time measuring something that's insignificant, all right? You want to measure things that are important for the performance of your system. Calibration. What equipment do we need and what kind of calibration do we need? And we want to make sure everything's calibrated properly. Otherwise, you're gathering data that's not has not been basically considered truthful data or data that you can basically depend on because your calibration, let's say your multimeter or your thermal test chamber was not calibrated properly. It was reading 100 degrees Fahrenheit, 100 degrees Fahrenheit inside the chamber. In actuality, it was 125 degrees Fahrenheit. So those are the things you got to watch out for. What requirements are we testing to? I mentioned this earlier that you got to be thinking about the requirements and which ones you really need to be testing to. Typically, they're performance requirements. And how are we going to do the analysis? How much analysis do we do? You can do what they sometimes call, you can get into analysis paralysis. You can keep analyzing this thing to, till you enter your career. And so you got to figure out how you're going to do the analysis. How much data do I need? What data do I need? And how am I going to do the analysis? And then, this relates to the unit, the box, avionics box, or the computer system, whatever you want to call it. You're going to be unit testing, development testing. So development testing deals with early testing. Going back to the beam model, it's on the left-hand side where you're doing development testing. You're going to be doing integration testing, systems testing, regression testing. Regression testing usually is associated with software. Once you've done any upgrade to the software that's already been under what we call configuration control, you got to run a series of tests to make sure that that software did not corrupt your system. That's part of regression testing. Human in the loop testing. Again, if you're modifying your interface, you're always checking to see, did we make it where it's more difficult for the person to use this system? Qualification testing. All right, so qualification testing is a huge effort at NASA. It's basically you're verifying the design life of the system. So you're exceeding a lot of the parameters of the system. You're stressing the system, but you're saying that once we finish this qualification test, my system is designed for 5 missions or 10 missions or 15 missions. Acceptance testing is associated with workmanship. Has this system been built right? with no errors. Okay, so there's two things that you're doing during acceptance testing, and even to some extent qualification testing, because before you start doing qualification testing, you got to do acceptance testing on the system. In other words, you want to make sure that before you start qual testing, this box was built correctly with no manufacturing errors. And so the acceptance testing basically looks at manufacturing to see how well they're manufacturing the system. Bad solder joint. This wire was these two wires were swapped. Things of that sort. Those are some of the things that you're looking at. Test readiness review. I mentioned this earlier. You know, you're looking at all the aspects for a particular test, whether it's a system test, a unit test, not so much development test, an integration test, qualification test, acceptance testing. You want to look at are we ready? Do we have the people involved? Do we have the chambers ready? Are they calibrated? Do we have all the instruments ready? All these kind of things. This is part of test readiness review. It's a major review before we start doing testing. Cost of an error. You may have seen this. Early on, it's cheap. You can just you're not under configuration control. You can change your requirements, and it's not too costly. But as you start going further into your phases of your project, it gets more and more expensive. More expensive. So you do your prototype, your development testing, your device verification test. Device verification test basically means you're doing some of the qualification testing with a unit that's not under configuration control. That gives you a lot of freedom, because once you're under configuration control, you got safety people, you got the quality assurance people all over you, and so they're checking to make sure that you're performing every step in a what we call a work authorization document, or sometimes a technical procedure sheet, uh, making sure that you're following every step along the way. And it's a pain. It's a pain. So if you got the freedom to test, to make changes in that kind of freedom environment, that's the best time to do that. And you got to do that early, because once you get to run for the record, which happens further down after, especially critical design review. After critical design review, things start getting very, very expensive. And so you're trying to minimize uh, errors at that point, because it starts getting extremely expensive to make changes. And human in the loop testing, early and often. I can't emphasize that more and more. I have to say, unfortunately, engineering schools, uh, I don't know in Puerto Rico, but in Texas and some of the other universities, colleagues of mine that went to different universities, how much of they talked about humans and testing? Zero, zip, nada. Uh, they basically, it was just the hardware and software. There's four components you always have to be thinking about as an engineer. You're thinking about the hardware, you're thinking about the software, you're thinking about the environment that the hardware and software are going to be residing in, and at equal level is the human. All right. So from those four that I gave you, which three are deterministic to the most part? Hardware. That's pretty much the deterministic. You design a system to operate in a certain fashion, and so it's going to, you can determine how it's going to operate. Software, you can also determine how it's going to operate for the most part. The human, or rather the environment, you can predict what the environment's going to be. The human, non-deterministic, very difficult to figure out how that person's going to feel that day, how they're going to operate the system. Very difficult. All right, so if you're not testing, it's going to get expensive. Complexity of the system, the testing processes, and equipment to test new technologies. Complexity makes it likely that some essential features going to be overlooked. This is from Perro, and he put it right on the button when he said that, because its complexity keeps increasing. Number of components, connections. Look at here's an interaction diagram. As you start having more interaction, you can call these people, you can call these components, you can call this hardware, you can call it software modules. As you start getting more and more of these, look at the amount of interaction. So there's a likelihood that you could miss something in a test. Number of requirements and complexity. From a human perspective, how hard is it to understand this system? I like this Dilbert cartoon. It says your user interface requirements include 400 features. Do you realize that no human would be able to use a product with that level of complexity? And so this manager that probably has never worked with people and humans says, good point. I better add easy to use to the list. All right, so you just had 401 components. So as your complexity increases, the verification increases exponentially. And guess what? And so does your costs. All right, test like you fly, fly like you test. It's a systems engineering methodology focusing on the validation of systems' ability to perform its mission. It's mission-centric versus requirement-centric. Requirements are individual requirements that you're verifying. The system shall operate from minus 40 to 150 degrees Fahrenheit. That's one individual requirement. But a mission-centric requirement is something like the system shall launch from Kennedy Space Center to the space station and dock within 54 hours of launch. Okay, so that's a mission-centric requirement. Requires more involvement in verifying a lot of requirements to get to that point. The process was created based on lessons learned. People early on during this, especially the 50s and 60s, they did not do mission-centric type testing. They did requirements testing, individual testing, and that basically burned them. So the concept of operations is one of the things that helps you figure out test like you fly, fly you test. How are you going to operate this system? Here's the profile of a launch from Earth, and you go to low Earth orbit, moon orbit, asteroid. You're going to go from the asteroid back to lunar gravity, and then so on and so on. And so here's the concept of operations. And then what's the time sequence of the systems events? You have a nominal where things operate perfectly, systems interacting back and forth. You have an off nominal case, but you also have a contingency case, and you have to factor in the emergency case. Even though the emergency case, for the most part, is not considered a lot, but it's one of the most important because you want to know how to get out of town, so to speak, if something goes wrong with your spacecraft. And then the test strategy at the box, subsystem, system level represents representation of the actual systems flying. Ensure the the test and support equipment is representative of the actual system and represented stimuli to the system. What is feasible and practical to the test? There was a project many years ago, and I'm not going to name the project, but they did ground testing with a certain particular power supply that was off the shelf. And so it was not the actual power supply for the flight system. And so they were getting a certain response from the avionics box. In space, this avionics box went berserk. And what happened was that the power supply ramp up voltage, the power supply characteristics of that actual flight system was not representative of the actual ground system. And so they failed to consider that aspect of the characteristics of the ground system versus the flight system, and they had a failure. So you got to be cautious about that too as well. You don't just say, I'm going to go get a power supply from, I don't know, Radio Shack or Amazon.com, and we'll just test it like that. You got to be, this requires thought. There's a lot of thought, systems thinking, as I call it, as part of the engineering process. Benefits of testing the Apollo spacecraft. I was lucky to know quite a few people from the Apollo space program, and design, configuration control was a biggie. Understanding all discrepancies during tests, but testing was one of the big things that was a success factor for the Apollo space program. They got a high reliability through all the environmental acceptance testing. They tested over 11,500 vibration tests, just that alone. And they had 5% failures, but they were able to figure out what went wrong. A total of almost 4,000 acceptance thermal tests with a 10% failure. Most environmental test failures occurred in electrical, not surprising, 57%. But the important thing here is that the testing basically fleshed out all of the issues. Hundreds of hours of human-in-the-loop testing, 200 hours of lunar module simulation to get the right human interfaces correct. Think about if you ever saw Apollo 11, what happened when they were getting ready to land. The computer, the Apollo guidance navigation computer, was overloading, and so Neil Armstrong had to shut off the autonomous system and take over manually to land the spacecraft. Otherwise, they were going to crash. So you got to do all that kind of testing. You got to do a lot of what ifs. You know, I have to say, systems engineering, it's a big what if, asking what if questions, a lot of what if questions. If you're not asking questions, there's something wrong. Ariane 5 failure, okay? So I'm going to just kind of briefly go through this. What happened was that the Ariane 5 was using some of the Ariane 4 software for the navigation system. And the Ariane 4 was a smaller, slower rocket than Ariane 5. And so what happened was there was a overflow, and it went into a what they call exception handling. But the designer did not put exception handling, and they did not test the software for the Ariane 5. Again, the programmer for Ariane 4 decided this that the velocity figure would never be large enough, made an assumption, bad engineering, making assumptions without defense or evidence of that data. And there he said, I don't need an exception handler. Well, it crashed. So Ariane 5 was a faster rocket than Ariane 4. And so the point here is that you just don't do, and what they did here was they did verification by similarity. They said our software for the guidance is going to operate on Ariane 5 because it worked on Ariane 4, and that was just really bad engineering. So the cause was both a requirements omission and a failure to test reuse software that was already used on another spacecraft. Mars Polar Lander. So this one here basically was launched in '99, supposed to land on the South Pole and dig for water or ice with a robotic arm. It crashed. All right. And what happened was that it was a possible premature engine shutdown due to transient noise on the lake sensor before spacecraft landing. It shut down about 40 meters above the surface, which came coming down at 22 meters per second. So it crashed. It crashed. And the cause of the error, there was a couple of things that were associated. One was an improperly censored wiring, and the other one was an orphan requirement. If you look at this little box, it was one requirement. I'm sorry. Number one had two requirements, which is bad requirements writing. You never have two shalls in one requirement. And that's what they had here. They had basically two shalls. So they missed the second shall that said that the touchdown sensor data shall not begin until 12 meters above the surface. And so the designers did not see that requirement. They didn't design for that. And hence and then the unit testing, they never tested for transients, and so it crashed. So you had lack of testing and an orphan requirement. Orphan requirement meaning that there was no flow down from that requirement down to a lower requirement, so they could write code for it. But again, it was two shalls in one requirement, which was bad engineering. And no industry is exempt from failures. You know, the Deepwater Horizon, they failed to test the cement, whether it was adequately controlling the hydrocarbons going back up to the top, and as a result, there was an explosion. Toyota, unintended acceleration. Large number of functions were overly complex and untestable. We had some NASA folks involved with that, and they said that the software was spaghetti code, very difficult to create a test test scenarios based on trying to figure out what this code is supposed to be doing. Um, Technical performance measures. So, right. So this is to show how well a system is satisfying its requirements and meeting its goals. And so you have something like this that you sometimes report if you're the systems engineer or project manager, and you're looking at the plan profile. That's the green line right here. And then you're looking at the tolerance band. What's minimum accepted and what's maximum accepted. All right. And there's your threshold. And so this is how you're doing your technical performance measurement. It's reviewed periodically. It provides visibility to actual versus planned performance. And it gives you also an early warning if this system is not going to meet the requirements. And so what are some of those technical performance measures? Weight is one. Power, heat load, reliability from a system, subsystems performance standpoint, range, latency, accuracy, throughput, memory storage. There can be a whole list. It all depends on the mission that you're designing for. And then final words: plan for testing early in a program or project. Ensure the realistic cost estimates to plan and execute testing for early detection and correction of developmental deficiencies. Again, it's just not designing a system, but thinking about what ifs, going back to the what if scenarios, okay, and factoring that into your cost estimation. Development testing to show that a system can be built and operated. All right, you can build something, but it may not operate. All right, so you got to be sure that the design and manufacturing is there for building and operating the system correctly. And there's three possible outcomes of a test. The test results match expected outcome, test results don't match expected outcome, and test results are not understood. And only one of this is good, and I think you know which one. And then without good test measurements, it's hard to determine how well the system is performing in the anticipated environment. What are my design margins? When I've been involved with PDRs, preliminary design reviews, and critical design reviews with contractors, if I'm not seeing any design margins in the design, I ask them, what's your design margin? Did you design this just to meet the acceptance requirements? And if they say yes, and that's a bad answer. All right. Did you design this computer system to handle um, more than 14 inputs, things of that sort? So design margins. What are those design margins? Is it meeting requirements? Remember, the requirement without a test is just marketing. It's just blowing smoke. All right. And do we have a risk to the program? What are the risks? Okay, what are the risks in terms of testing? What are the risks in terms of the testing, in terms of the verification and validation, maturity of the technology? Skipping tests to save work and money and to be successful is not going to work. And unfortunately, some project managers sometimes look at dollars and not, let's say, looking at the integrity of their job, looking at the integrity of their company and credibility as well. And so that's basically it. And I'm going to stop sharing. And at this time, I'm going to exit out of here. And let's see, hopefully go back to Wilbert, and I'll start answering questions.
Well, thank you a lot, Salazar. I've been impressed, and I know everybody here is really impressed with what you just talked about. We certainly learned a lot about systems engineering, verification, validation, and flight certification. So right now, if anybody has questions, please write them in the chat, and George will be answering them. I do have some questions of my own, but I'm gonna leave them for the end so that you guys can participate first. So go ahead. Any questions that you want to ask George about what he spoke about today, or maybe about his career? As I mentioned at the beginning, he has been at NASA for more than 35 years, so he has plenty of experience with different systems, such as the space shuttle, and most recently with the Crew Dragon. So I know that you guys are really interested in learning about that. So here's your chance. Go ahead. You can also write me by the WhatsApp chat, or maybe try to mute yourself. I'm not sure if Kelby changed the permissions to mute yourself, but yeah, go ahead. We have a question, George.
Okay, so what was the favorite part in testing with Crew Dragon? Uh, um, well, so my responsibility was the control panel, and so the control panel was the panel that commanded the spacecraft. And as you probably saw in some of the videos and photographs, it was a touchscreen. First time a touchscreen has ever been flown in space. So I have to say that it was very. I was very excited, to be honest with you, because I've been accustomed to the old traditional displays and control systems like shuttle station that they use a lot of switches, and so the SpaceX touchscreen was new, and so I was really I was involved with a lot of design reviews, and but I was excited, because I was hoping to see this kind of technology in space, and the SpaceX did a heck of a job, to make this happen. See, let's see, how user friendly are the panels? Okay, so user friendly is a bad requirement. You can't verify user friendly because it's very nebulous. But from the standpoint of uh, let's call it workload. Okay, so from a human factors engineering, I mentioned it, human systems integration, human factors engineering. One of the things that human factors engineers look at are two things: the usability of the system and the workload. All right, if it's not usable, the customers or the users, or in this case the astronauts, are going to tell you, "Hey, this thing is just hard to use," and so. It took a lot of iterations. I showed in my presentation, and I kind of was uh, I didn't show more errors than I should have, but there's a lot of human in the loop testing to get the interface correctly. So but in the end, once we went through, oh my gosh, somewhere in the vicinity of maybe 20 25 user interface testing. We got the displays just right and everything, and so it was easy. It was a lot easier for the astronauts to use the system. So, what do you enjoy most about your job? So, this is a good question. So, I have to say, at this point in my career, is gaining all this knowledge and sharing back to students. That's the part that I really enjoy. I wish I could do this outreach stuff full time, but I'm basically I'm doing SpaceX now, or the Crew Commercial Crew, and now I'm getting involved with Artemis. With the human lander system on the moon. So I'm kind of excited with that. But I have to say that sharing knowledge with students is the part that I enjoy about my job, and trying to make it as simple as I can, because I have to say that the professors I had in school. Um, um, this is my opinion, that they wanted to make it look so hard, so you wouldn't ask them questions, or make it look so hard that you wouldn't do very good in testing. And that's not the way I feel. I think engineering, you need to learn early on what it really takes, to do system engineering, systems engineering, if you're going to get into systems engineering. So that way, when you come out of school, you feel more comfortable, and that's important. Feeling comfortable going to work for a company, whether it's, I don't know, Tesla, going to work for SpaceX, going to work for NASA. You feel very confident because you understand some of the limitations and challenges of engineering systems. Let's see. Let's see, what is the most common mistakes or issues when it comes to testing and validation in a spaceflight system? Oh, there's a lot of, uh, there's a whole bunch of that, but the most common mistake is misconfiguration of the systems. They didn't configure the system right, and the wrong software load. That goes back to configuration management. They didn't have the right software in the system. They didn't have the right version of the tests, what we call ground support test equipment. And so the tests, they went through 5 or 6 hours, and they go, my gosh, this data doesn't make sense. They go back and look, oh my gosh, we misconfigured everything. And so that happens over and over again. And it's understandable, because sometimes it has to do with pressure. And so you got a lot of pressure. You got pressure to launch at a certain time, but that should not distract you from making sure that you've cross your T's and dot your I's in the program. Let's see. What extra steps or verification will be needed for future transportation systems like starships that do not have an abort system, compared to the process of certifying Dragon a Starliner? Oh my God! Wow. Okay, so that's a big mouthful. That's a good question. So here's the thing: as we go deeper into space, we're going to have to depend more on machine learning. We have to depend more on artificial intelligence systems, because basically those type of systems are going to represent mission control center. Because right now we're not too space station. It's only 250 milliseconds away from us as far as communicating from a communication electrical standpoint. If we go to the moon, 1.2 seconds, not a big deal. All right. We did it in Apollo. Going to Mars, 20 minutes, 40 minutes, that's a big deal. Something going on with that starship, something going on with the systems, you cannot depend on mission control, because you gotta have an answer now. And so we're gonna have to have um, artificial intelligence and machine learning. But here's the thing: how do we verify those kind of systems that are learning all the time? Verification and validation for what we do right now is with systems that we call deterministic systems. We know how they're supposed to operate. And so many times we design testing to see if it responds in a deterministic manner of how we know how their systems operate. When you're dealing with machine learning and when you're dealing with artificial intelligence, this thing is learning all the time. So how do you verify a system that's changing on you consistently? That's one of the big challenges for things like going, to using starships, to take us to other planets. So Dragon, Starliner, deterministic systems for the most part. What's the most challenging thing you've done on the field? Let's see. What's the most challenging thing you have done on the field? So I guess you want to say the most challenging thing maybe that I've ever been involved with. On X-38, I was responsible for the flight computers, and that was rather challenging, because it was challenging my technical knowledge as far as developing avionic systems. The X-38 required five flight computers, and the heat generated by those flight computers was quite a bit. And so I had to deal with going back to my thermodynamics class that almost kicked my rear. Was how do you dump somewhere in the vicinity of 1,500 watts of power into a cold plate? Supposedly they called it a cold plate that basically was at 125 degrees Fahrenheit. So a cold plate that's at 125 degrees Fahrenheit, there's two things that you can do. One is increase the size of the cold plate. But if you increase the size of the cold plate, what does that mean? More weight. More weight, what does that mean? Larger volume. What does that mean? Larger spacecraft. Larger spacecraft, can we launch it? Okay. So again, systems thinking, how one thing can affect other things. And so the idea came up that we had to increase only the weight of this box, and that's what we did in order to dump the heat into the cold plate. But it was very challenging. Let's see, what are you planning to do in the near future or work on? I just got assigned about a month ago to the Artemis program. I'm going to be working the human lander systems for the crew. So that's but I'm still working SpaceX because Crew 1 is coming up on let's see, October, mid to late October of this year. So that's going to be Crew 1. Crew 1 is going to be the first ever. This is historical. It's going to be the first ever commercial spacecraft that takes astronauts to the space station. Okay, so demo 2 was just a demonstration of the capabilities. They had to do demo 2 in order to do validation. Okay, so there's something I didn't mention about. Sometimes validation cannot be all done on the ground. Sometimes you have to launch a vehicle to do the validation, the rest of the validation. And that's what SpaceX did for demo 2. They did the rest of the validation. And that's what we're going through right now, is looking at the data to see if they met those requirements. All right. Oh, good. That was a good question. Let's see. Even after testing and meeting all requirements, do you sometimes wonder if something could go wrong? Yeah. Yeah. I mean, something can go wrong, but I mean, you try to plan as much as you can. I love people that like to ask, what if? What if this happens? What if that happens? You can't just think of the success that things are going to work hunky dory. What if this fails? Okay, what if this box fails? What if we lose attitude control? What if we lose guidance navigation control? You have to look at the whole system. This is part of systems engineering, systems thinking. Is you look at the holistic thing, and then you start looking at, you start throwing darts, so to speak. What happens if this fails? What happens if that fails? And you look at, okay, if the failure happens, do we have something in our system to recover, or at least get the astronauts home? That's the bottom line. We want to make sure that the astronauts are safely returned home. That's a good question. Uh, did any of your projects go wrong at some point? If so, how did you solve it? Let's see. There was one project that went wrong, and it had to do with actually what happened. Going back to the human, is that the crew member was really tired. This was a speech recognition system. The crew member was really tired, and so they tried using the system, and their voice changed dramatically. And so we failed to consider, um, let's call it safeguards, when the astronaut's voice was tired. All right, now. If we had the technology that exists right now, we would have had some kind of let's call it artificial intelligence to analyze the astronaut and basically determine how well will this system work with the way this astronaut is talking right now. And so we could have said, hey, don't even try using the system right now. You're not in any shape for doing that. So let's see, for those interested in testing process and mentality in the RMS and what of the aerospace industry, especially, which topic classes are the most useful? Let's see. So if you're interested in testing and and learning about that for aerospace, and not just that for aerospace, I mean, I'm hoping that maybe it's typically under systems engineering, and the term is sometimes used test and evaluation, testing and measurement, but the whole subject of testing should be taught, and this is my opinion. If you're going to take a class on testing, it should be taught. It should be taught by a professor that's actually done testing, because what you see in the books is sometimes not what really happens in the real world. And so you need to have somebody that said, "Yeah, I've done this, and you know what? This did not work because of this, this, and this." So I can tell you that in some of the books that I've read, and I've read many books on systems engineering on testing, they talk about test setup and blah blah blah. The ideal world, but as I've come to learn, the ideal world is not ideal in systems engineering. Things like misconfiguration, wrong software. You know, the sensors were not calibrated properly. Personnel were tired and they misconfigured a system. Personnel did not activate certain switches. Personnel did not, you know, the list goes on and on. There's things that just don't show up in books. Okay, you learn this through people that have actually experienced this. Let's see. Do you know of any good internships where students can learn more about systems engineering? Uh, you know, that's a good question. And so, you know, there's two kinds of internships, and I'm just talking about NASA, but in general, if you're looking for an internship, whether it's NASA or somewhere else, look for words that talk about systems engineering and be cautious because some companies basically say they do systems engineering and they don't. And I've seen that where, you know, you go and you say, you know, we're looking for a systems engineer, you know, to handle our computer systems. And then if you read it, it's basically IT stuff, information technology, you know, networking, programming, configuring Ethernet cards and stuff like that. And you know, to some extent, that's a little bit of systems engineering, testing, whatever you want to call it. But real systems engineering involves requirements, it involves trade studies, it involves you know, looking at the V model. Look at the V model. That's systems engineering. And so, you know, some of the things that you look for in in some of your internships. And if you can come, if you get a mentor that's done systems engineering, you're going to be way ahead of some of your student colleagues. Okay, what has been the most stressful project you worked on, and how did you handle the stress? How did you start your career? Okay, so um, the most stressful project was, I have to say, uh, um, space shuttle. We had some problems. I was responsible for the modular auxiliary data system, which was a data acquisition system on the shuttle, acquired about 2,500 to 3,200 sensors of data, and it was recorded. And so we were having some difficulty with some sensors, and we were under the gun and pressure from the program to resolve that. So I was working with Rockwell Downey at the time, which became Boeing, and you know, I just had to figure out a schedule to, you know, to come up with a solution for solving those sensor problems. It was a bit stressful, to, you know, to say the least. How did I start my career? Oh, I there's not enough time to talk about that. You know, some people, you know, start from point A to point B, and you know, I'm a little kid. I want to become an engineer. I want to go work for NASA. Straight line. Mine is wiggly, all over the place. I worked in construction. I worked in bakeries. I worked, and you know, I didn't do well in school. I graduated 475 out of 605 high school students. But I, somehow I was able to come to work for NASA. That's the bottom line. It was not an easy. It was not an easy path. It was not an easy path. A lot of challenges. Um, let's see. What advice would you give to a person planning to enter this field of study? Uh, you know, one of the big advices I have for you know, if you're going to do systems engineering, you're going to do test and evaluation. Is if you can, is to hopefully select professors that have done this, you know, because that's important. It's the book learning is okay, but I have to tell you that it's the real world experience that you'll benefit from.
All right. My question is more on the technical side. You and I work with the human in the loop testing for Empress quite a bit. And in that project, for context, we had the challenge of having a really short timeline. We had like 2 or 3 years to propose and do this project. And now I'm wondering, how is NASA managing the human in the loop testing with all this new hardware that is coming out for the Artemis missions, particularly the Artemis 3 mission, which we'll use for the first time, the human landing system? How are you guys planning on integrating the humans in the loop testing? I recently saw a video that the national team delivered a mock-up version of their lander, but I was wondering, what other steps are you taking to ensure that the human in the loop testing is going to be done successfully for the Artemis missions?
Well, okay, so that's a good question. So human in the loop testing, there's a um, end objective to meet, and the end objective is usability and satisfaction. There's a third one associated with workload. And so from a human factors engineering standpoint, there's a rating associated with a interface, and so they have to meet those ratings. Okay, and that's part of the testing. Um, and I think one of them is called the Bradford test for usability, and so you have to score something like less than 5, and it's been a while, but there's some scorings that are associated with that, and that's what the requirement is going to be for human in the loop testing, and that's what when they're designing the system, they're going to have to design it to ensure that it's going to meet that requirement. And it's just not for one person, it's for many people, because you're going to have a diverse set of people. You're going to have females, males, um, and in different situations. And so, you got to test and test and test. And making sure that it meets those particular scale requirements that are necessary to say, from a human systems integration, human factors standpoint, human computer interface standpoint, that this system is acceptable for flight.
Awesome. And now the final question, and then you can make some final remarks. We, of course, have the perspective of the audience when seeing the Artemis program, but what is the perspective of the Artemis program from a NASA employee or from somebody that's working with this program on the inside? In this case, your perspective of the Artemis program.
My perspective of the Artemis program. There's a lot to do in a short period of time. And so, things are going very fast. That's one of the things that's a little bit, talking about stressful and nervous, is that I kind of feel like they tell me to jump on that horse that's running at full speed, and I'm supposed to grab it, climb it, and jump on it while it's going full speed. So that's my challenge, is to get up to speed. And I've been in that situation before. So the challenge right now is that things are happening very quickly, and I'm it's I think in about I'm gauging it in about a year. We'll see where NASA's at as far as meeting the requirements. There's many things there's a lot of dependencies. Obviously, the space launch system that's being developed by Marshall Space Flight Center in Huntsville, Alabama, is a dependency, because that's the one that's going to launch the Orion spacecraft. And of course, the Orion spacecraft, there's a dependency there because Orion, the mission 1, Artemis 1, now they're calling it, is an uncrewed mission that takes the capsule around the moon. It spends like 20 days or something like that, and then come back to Earth. So that's going to be a demonstration or validation of several requirements. So from my perspective, I'm involved more with the crew interfaces, and so that I have to focus on that and make sure that lines up with the schedule. But obviously, you got all these things happening, and so I got to be watching that and seeing where the alignment or misalignment is happening, and bring that to attention to to folks that are kind of the uh, higher up people in the program.
All right. Well, thank you, George, for taking your time to talk to
Sure.
us today. It's been great. We've learned a lot, as I said, and we hope to see you soon working with us in our projects. And hopefully, when things get better, you get to come to Puerto Rico and spend some time with us here at El
Oh,
Colegio.
I would love it. I would love it.
That will be amazing.
Yeah.
So everybody that has been watching this on YouTube or has been in this Zoom call, also thank you for being with us tonight. And be on the lookout for the other space talks that we will be giving throughout the semester. And have a good night, people.
Okay.